Hello everyone. Today we're going to present our PBL project titled PCB Track Defect Detection. Let me introduce myself. My name is Selfiana Aktasia, and our group members are Syafina Hikmalia and Mita Rivawati. This project is guided by our project manager, Mr. Abdullah Sani, SST, MSc. So I'm going to start by explaining the background of our PBL project. The quality of an electronic circuit depends on the quality of the printed circuit board, or PCB. However, PCB inspection is often still done manually, which causes problems with accuracy, speed, and consistency. To solve this, we propose an automatic defect detection system using machine learning, specifically the YOLOV 12 algorithm, which is fast and efficient for object detection. This system is designed to detect PCB defects quickly and accurately to improve manufacturing quality. And then this is the system explanation of our project. In this project, we use YOLOV 12, the latest version of the YOLO, You Only Look Once, algorithm. It offers better accuracy and speed, especially for detecting small PCB tracks. YOLOV 12 is used to detect different types of PCB defects based on images from the dataset or captured directly by a camera. The main steps are data collection, pre-processing and annotation, model training, classification and detection, and finally, model evaluation. This process helps the system detect PCB defects automatically and efficiently.
This dataset is from Kaggle, and some additions from what we made in PCB. The purpose of this section is to collect and categorize images of defective PCBs that will be used to train the detection system. There are 6 main types of defects commonly found on PCB tracks, namely open circuit, missing hole, mouse bit, short, spur, and spurious copper. Collecting images for each type of defect is important to ensure that the detection model can recognize and classify them all accurately.
This slide shows the PCB design we created using EasyEDA. This PCB was made as a test object that includes several artificial defects, such as missing hole, open circuit, short, spur, mouse bite, and spurious copper. Each defect was placed intentionally and precisely in different areas of the board to represent real defect conditions that often occur in manufacturing. The board is arranged in a panelization layout, meaning one panel contains multiple sections with different defect types. This design allows us to easily capture and test various defect patterns under the same lighting and camera conditions. Later, the same PCB will be used to validate the YOLO V12 detection results in real time using the camera system.
Next, design the physical structure and camera layout to ensure stable and high-quality PCB image capture. Design specifications: frame, made of aluminum profile, base plate uses acrylic. Base dimensions: 20 by 20 centimeters with 2 centimeter high legs. There are 4 millimeter holes on the platform for PCB placement. Camera support: 20 centimeters high with a 10 centimeter overhang to the front, so that the camera is directly above the PCB camera, using a megapixel USB camera.
This slide shows the initial concept of the Graphical User Interface, or GUI, that we plan to develop. The main function of this GUI is to provide a visual platform where users can easily monitor the detection process carried out by the system. Through this interface, users will be able to see the PCB inspection results directly once the system is connected to the camera and the trained model. It is designed to make the overall detection process more interactive, practical, and easier to understand compared to manual observation. In the future, this GUI will also serve as the main access point for operators to view or validate detection results in real time. Want to see a full demonstration GUI of PCB track defect detection system in action? Click this video now, or visit our YouTube channel at Papanaga with us to see more of our projects. In the next stage, our team will print the PCB design that we have created to be used as a test object. However, since the mechanical materials, including the camera, have not yet arrived, the process of capturing image data from the designed PCB cannot be carried out for the time being. While waiting for the materials to arrive, we will utilize the time to train the YOLO V12 model using the dataset from Kaggle that we have previously prepared. This step aims to allow the model to learn the general patterns of PCB defects before performing further training with image data captured from the camera. By doing this, the development process can continue productively, even though the hardware components are not yet fully available.
In conclusion, our project has successfully completed several stages, including the mechanical design, PCB defect path design, and dataset collection. The next focus will be on training and evaluating the YOLO V12 model, so the system can automatically detect PCB defects with high accuracy. Thank you for attention. See you in the final video of our project.